Welcome back. Another day, another machine learning module, eh? In this lesson, I want to take a brief minute to talk about what we're going to do in this section. So far, we've covered one machine learning technique, namely linear regression, and this was with one variable only. And also, we worked through the fundamentals of the Python programming language. So where do we go from here? Well, before we dive deeper into the next projects and tackle more complex machine learning techniques, we've got to peek under the hood and kind of get an understanding of how machine learning actually works. I mean, how does the learning in machine learning actually happen? What are the steps involved? And how is it that we can give our computer a whole bunch of data and get back these beautiful parameter estimates? How are these calculations actually made? And to answer these and other utterly fascinating questions, we're going to have to get our hands dirty with some mathematics and some algorithms. And this means getting comfortable and working through a couple of difficult concepts. And that includes this idea of optimization, mathematical optimization. So you've probably already guessed that this section is going to be a bit more technical than the previous modules. We're going to be doing some calculus. We're going to work with derivatives and partial derivatives. We're going to be doing some more advanced programming Python too, because we're going to be using loops and we're going to write our own optimization algorithm from scratch. And the optimization algorithm in question is called gradient descent. And once we've done all that, we're going to apply this algorithm to various problems and see how it behaves. And what I mean by that is, in what situations does the algorithm do well? And when does this algorithm fall flat on its face? What are the strengths and weaknesses of the approach? What is the algorithm sensitive to? And does our algorithm have an allergy to peanuts? And all this will help us build an understanding of how machine learning actually works from the ground up. And if we want to be able to understand the more complex machine learning techniques like neural networks and tackle the more difficult projects, we're going to have to build up an understanding of how these techniques work to arrive at a solution in the first place. And that about covers the intro. So how does machine learning actually happen in practice? I mean, it can't just be magic, right? In this lesson, you and I are going to establish a useful framework for thinking about machine learning techniques. This is going to be our basis for thinking about the gradient descent algorithm. So at the most basic level, what we're doing is feeding a whole bunch of data into a computer and it gives us back some solution, some answer. The thing that our computer is actually learning is the relationship in the data. So how is it that we can feed a whole bunch of data into our Python program and our program spits out a function that describes the relationship in this data? What are the steps involved in how our machine learns this mathematical function? In a very simple linear regression example, our machine learning program has had to learn the orange theta 0 and the green theta 1 parameters in this equation. And that's going to be on the basis of the data points that it was given. So you can keep this example in mind in what I'm about to describe to you, but this framework that we're going to talk about goes well beyond regression. And that's because many machine learning techniques follow pretty much the same three-step process to arrive at their solution. And here it is. Step 1 is to make a prediction. Predict what exactly? Well, the coefficients in our function, for example, the theta 0 and theta 1. Our machine is learning a function, so it has to start by predicting the coefficients in that function. Now, the very first time this happens, the very first prediction is pretty much like a completely random guess. So let's move on to step 2. After making the prediction, step 2 is calculating the error. In other words, we need to measure how good the prediction was. We need to calculate how far off we were from the data. And that's why we calculate the size of our error. And step 3 is the learning step. This is where we adjust our initial prediction. And this is the crucial part, right? First, we made a prediction. Second, we compared our prediction to the data. And now it's time to learn from our mistakes. Yeah. Having figured out how far off we were in the previous step, we can now make a change to the coefficients. But we're not done just yet, right? This was only the first run through. At this point, we're going to go back to step 1 and make a new prediction. This new prediction is going to have our modified coefficients. So using this new prediction, we once again calculate how badly we did and calculate the error. Hopefully, this time round, the error is smaller than the first time round. So having measured the error and how badly we did, we adjust our prediction once again. And then rinse and repeat. So in summary, there are 3 steps. Number 1 is predict or infer the theta values of the function. Number 2 is calculate the error and measure how far off we were in our prediction from the data. And step 3 is making an adjustment to have a smaller error the next time round and slowly learn the best coefficients. And this is the learning process. When we're writing our Python code in this module, this is how we can think about training our machine learning model. Now, there's actually a name for this kind of step-by-step approach that we just described. This is called an algorithm. An algorithm is a set of instructions for solving a problem. The Cambridge Dictionary defines an algorithm as a set of mathematical instructions or rules that, especially if given to a computer, will help calculate an answer to a problem. You know, the thing is, you and I probably more familiar with a different usage of this word, right? Having heard sentences like, my app uses an algorithm to predict if fans of one particular band will also like music from another band. So it's perfectly understandable that most people think that the word algorithm is actually a word used by programmers when they don't want to explain what they did. So before moving on to the next lesson, I'm going to leave you with a fun fact. The word algorithm actually gets its name from a guy, right? Muhammad ibn Musa al-Khwarizmi. Al-Khwarizmi, algorithm. Now, I probably didn't pronounce that right, but in 1825, 1,200 years ago, this guy wrote a best-selling book in mathematics. And the Latin translators in the Middle Ages did an even worse job than I in pronouncing this guy's Persian name. So that's how we get stuck with the word algorithm. So anyhow, on that bombshell, I'll see you in the next lesson. All right, so previously, we've talked about the famous 3-step machine learning process. Predict, calculate the error, and learn. Now, the middle step is something that involved calculating an error. And I glossed over that part in the last lesson. So what does that mean, and how do we calculate the error exactly? So to provide a little bit of context, let's briefly revisit something that we talked about with linear regression, right? So here we had some data points, and our goal was to figure out which line best fits the data. In other words, we had to learn which line was best, because you could draw so many different lines through this data. And each of these lines, right, had a different value for the theta 0 and theta 1 parameters that are associated with it. So our algorithm somehow had to rank what the best values were for theta 0 and theta 1. So that word best is pretty vague, right? We need a hard criteria. So by best, what we actually mean is the line that minimizes the distance between the data points and the line. For example, this dark green line here is clearly better than this light green line below. Why? Well, because it's got a shorter distance between the line and the data points. So that's pretty easy to see visually. Now all we have to do is construct some sort of metric from that. What we need is a single number. And in this case, the number is going to look like this. What we're going to do is we're going to add up all the differences between the line and the data points. So the first difference might be 10, the second difference might be -6, the third difference might be 4. But because, a data point below the line will have a negative value, right? That -6, what we're going to have to do is square them. So we're going to square all these differences and then add them up. And now we've got a single number. And we've also got a goal, right? So we've got this single number that has a name. It's called the residual sum of squares. And this residual sum of squares gives us a single metric on how good our estimates for theta 1 and theta 0 are. So with this in mind, we know that we can find the best possible values for theta 0 and theta 1 by minimizing this residual sum of squares. So we've given our algorithm a goal. If the residual sum of squares for one particular line is equal to 100, then that's a better line than if the residual sum of squares for a line is equal to 500, right? The lower the number, the better our line and the better our estimates for these coefficients. So why am I talking about this? Why am I going on about something that we've already covered? Well, we can think about this number as measuring the size of our error and expressing how good or badly we did. And this brings me to this lesson's word of the day, namely cost functions. Our residual sum of squares, or how it's also called the sum of squared residuals, is, you guessed it, an example of a cost function. And a very big part of the machine learning process is optimizing for a solution that has the lowest cost. So finding the best solution falls under this broad topic of optimization. And optimization is actually a word that you'll come across in many fields, not just machine learning. So if this topic of optimization comes up across different fields, it shouldn't really be a surprise that this idea of cost functions is also something that you're going to see across different areas, right? So you'll find it in statistics, decision theory, computational neuroscience, operations research, engineering. So you see it in many, many places. And this brings us back to this topic of jargon and language, right? Because you have many different fields using different words for things that actually express a very, very similar concept, it can actually be a little bit confusing reading things or learning about this topic. So in order to make it easier, I want to introduce you guys to a lot of the jargon and a lot of the words that come back to this idea of cost functions right off the bat. So depending on the field and depending on the context, people don't actually always use the word cost function, right? And this can make things a little bit confusing, especially if you're reading an article online or a textbook of some sort. Sometimes you'll see these kind of functions being referred to as loss functions. And I've even come across people calling them error functions, but I think this is a bit less common, especially for this sort of application. And finally, you might even come across the term objective function. So in the process of optimization and trying to find the best solution for something, you'll often find the words loss function and cost function used interchangeably in many, many cases. But the word objective function means something a little bit more general, right? I mean, if you think about it, the objective isn't always to minimize the cost or minimizing some bad thing. Sometimes the objective might be to maximize a good thing. The relationship between the words cost function and the word objective function is kind of like how, I guess, like salmon is a fish, but not all fish are salmon. And I think that about covers the jargon, right? In machine learning, you'll mostly see the words cost function or loss function being used. And this is what I'm going to try to stick to in this course. Now, I don't know about you, but personally, I can't wait to jump straight into Jupyter Notebook and write some Python code. So that's what we're going to do next. We're going to take a look at how we can go about minimizing a cost function in practice. Stay tuned.